Hi, it's Deirdre Macnamara here, and in this set of slides we're going to take a look at statistical tests and why you need to use them and how you choose them. So for example, just sort of looking at a very simple scenario, you might be saying, where are you from and how do you like your steak cooked? There's sort of two questions that pop up, and we're thinking, is there any connection between the county you were born in and the way that you like your steak cooked? We have a feeling that there is a connection, and you might want to do a bit of research to find out, is there a connection between the county that people were born in and the way that they request to have their steak cooked? And you might design some piece of research that would actually look at this.
So you develop a hypothesis. Hypothesis is a statistical word. It's used in a lot of research, and it's important that you understand what these terms are. So hypothesis, another word in the language of English that you're more familiar with, is a guess. My guess is, my suggestion, the thing I want to check out is, first of all, we take a look at sort of opposing possibilities. So hypothesis 0 is always set to, there's no connection between whatever it is you're looking at. So in this case, between the steaks and the country or country that you're born in, hypothesis 0 is there is no relationship between the country of birth and the length of time you like your steak cooked. Okay. The opposite to that is hypothesis 1 is there is a relationship between the country of birth and the length of time that you like your steak cooked. Okay, and you're trying to find out which one of these is true. Is it hypothesis 0 or guess 0, or is it guess number 1? There is a connection between the two. Okay, so all pieces of research always start off with hypothesis 0, which means that there's no foundation to the thing that you're looking at. And hypothesis 1 is something, hypothesis 2 might be something else. Okay, and hypothesis 0 is always the null, nothing's happening here, hypothesis. Okay, statistical tests. The central aim of statistical tests is determining the likelihood of a value in a sample given that the null hypothesis is true, that nothing's going on. So H0, no statistically significant difference between the sample, for example Donegal, and the population Ireland, or between two different samples. Okay, so there's no difference between where you're from and how you like your steak cooked. H1, there is a statistically significant difference between the sample, Donegal, and the population, Ireland. Okay, and the significance level is usually expressed as a particular value. And you have to work out whether this is significant. Okay, correlations is another term that's often used in statistics. Correlation is the most commonly used and useful statistics. A correlation is a single number that describes the degree of relationship between two variables. Okay, is there a relationship between how you like your steak cooked and the county that you're from? So, relationships. While all relationships tell you about the correspondence between two variables, there is a special type of relationship that holds that the two variables are not only in correspondence, they work in symmetry with each other, but one causes the other. This is the key distinction between a simple correlational relationship and a causal relationship. Okay, let's look specifically at a correlational relationship. A correlational relationship simply says that the two things perform in a synchronized manner. Okay, they're synchronized in some way. For example, the relationship between the ability in maths, somebody's ability in maths, and their proficiency in music. It has been discovered worldwide that people who are good at maths are also good at music. Okay, and people who are poor at maths are often poor at music. Not every case, but in general a lot more people are good at maths and good at music, or weak at maths and weak at music. Okay, so there is a correlational relationship between maths and music. So as this is true, we can say that the two variables are correlated. They perform in a synchronized manner. so a synchronized manner. Okay, so carrying on then with correlational relationships, knowing that the two variables are correlated does not mean that one causes the other. So the fact that you're good at maths doesn't cause you to be good at music, or the fact that you're good at music doesn't cause you to be good at maths. Okay, for example, there is a correlational relationship between the number of steaks eaten in Donegal and the number of children born in the United States. Does this mean that if we want fewer children in the US that we should stop eating steaks in Donegal? Or does it mean that if we don't eat enough steaks in Donegal, we should encourage US citizens to have more babies? So does one cause the other? While there is a relationship between the number of steaks eaten and the number of babies, we don't believe that the relationship is causal. Okay? We have statistically proven that at times when Donegal is eating more steaks, there are more babies being born in America. Okay? So one always is synchronized with the other. We've spotted this, and scientifically we can prove this. But what we're saying here is one doesn't cause the other. This leads to consideration of which is a term that is often referred to as the third variable problem. In this example, it may be that a third variable is causing both the eating of steaks and the birth rate. Okay, and it is causing both of them, and we can see that that's making them correlated. For instance, perhaps the general world economy is responsible for both. So when the economy is booming, people in Donegal eat more steaks. When the world economy is booming, there are more children born in the US. So the third variable in this case would be the world economy. The world economy happens to be causing both the number of steaks being eaten in Donegal and also the number of babies being born in the US. So the key lesson here is that you have to be careful when you interpret correlations. Just because they're synchronized doesn't mean that one causes the other. Okay, correlations. In a positive relationship, high values in one variable are associated with high values on the other, and low values in one are associated with low values in the other. Okay, so for example, the example I have here is the number of years in school. So here somebody's having more and more years in school, and here's the expected salary. So what this is saying is the more years you do in school, the higher the expected salary. Okay, and the fewer the years you do in school, the lower the expected salary. This is a positive correlation. A negative correlation, or a negative relationship. A negative relationship implies that high values on one variable are associated with low values on the other. Okay, and this is sometimes referred to as an inverse relationship. The example I'm giving here is the more drinks per week, the lower the average marks in exams. So if this is a student and we're counting up the number of drinks they have per week, what we can say is, this hasn't been scientifically proven, but the more drinks that the person has per week, the lower the average mark in the exam. Okay, and you might decide you want to prove this statistically. Okay, so the average the marks the person has in the exam, on average the fewer the number of drinks the person is having per week. Okay, and that's considered a negative relationship.
Okay, so if we want to take a look at a correlation example, so for example, if you were looking at the relationship between two variables, for example, you've got a tour bus and you have people of different ages on the bus, and they're going around and they're stopping off in different restaurants, and you're looking at the amount that they spend on dessert. And perhaps you have some sort of hypothesis or guess that how old you are affects how much money you spend on desserts. So maybe you're thinking, oh, well, if you're older, you spend less or you spend more. You know, does age affect the amount of money you spend on dessert? Okay, so let's say we collect information from, for example, 20 individuals. And you're going to measure the age in years. That is a fairly obvious one. And the amount spent on dessert is measured based on an average of 10 restaurants. So you've gone to 10 restaurants and you're looking at the amount of money that each person is spending on the desserts. So we'll just show you the results results of that. So for example here we have the first person here was aged 68, and on average over the 10 visits they spent €4.10 per dessert. The second person was 71 and they spent on average €4.60. The third person, etc., etc. So we've got a variety of ages here. There were 20 respondents that you can see here, and here is the age or the amount that they spent on desserts in euros as an average over the 10 visits. So looking at one particular variable, we've got looking purely at age, we're looking at, there was one person who was 58, we've got frequency here, and age along the bottom. There were 2 people who were aged 60, we've got 3 people who were aged 62, 3 people who were aged 64, 1 person was aged 66, 68, etc., etc. So here's a simple histogram, just looking at one variable, and that variable is age. Here's the second variable. Okay, this is the average amount spent on dessert. So we can see here, so we've got frequency up here, and we've got the money down the bottom. So we can see that there were 3 people who spent €3.20. There were 3 people who spent €3.40. There was 2 people who spent €3.60. There were 5 people who spent €3.80, etc., etc. So that's another variable. Okay. Other ways of describing that data, we could look at the mean. So we've got age here, and we have the amount spent on dessert here. So looking at the means of the two of them, 65.4 was the mean, and the amount spent on dessert, the mean was €3.75. Okay, so standard deviation, which is showing you the variation, and then the square of your standard deviation is your variance, and we have that here. You could add them up, you can get a minimum, you could get a maximum, and we've got a range down here, which is the maximum minus the minimum. Another way of looking at it is a bivariate plot. Okay, so in this one here, we've both variables, we've age and amount spent on dessert displayed. Okay, so each of these spots represents a single person. So there was one person who was aged approximately 58, and they spent €3.20 or 30 or so. And the second person was aged 60, and they spent €3.10. And there was another person aged 60, and they spent €3.40. So you put a spot in representing each person, and you show their age up this way and the amount on average that they spent this way. And so each of those spots represents an individual who was recorded in the survey. So looking at these spots here, we can see that there's a kind of a pattern coming in the spots. And looking at it here, you can see there's a kind of a pattern going up in this direction here. So you should immediately see in the bivariate plot that the relationship between the variables is a positive one, because as we saw with the straight line going through the dots, you have a positive slope or moves up from left to right. Since the correlation is nothing more than a quantitative estimate of the relationship, we would expect a positive correlation. So, what does a positive relationship mean in this context? It means that in general, higher scores on one variable tend to be paired with higher scores on the other, and that lower scores on one variable tend to be paired with lower scores on the other. So specifically in this example, the higher the age, the more they spent. The lower the age, the less they spent. Okay, so higher age was related to higher spend, lower age was related to lower spend. Okay, and you need to confirm that this is true on your plot. Okay, so you can see that the means or the averages are different, and what you need to determine is that significant? So for example, you can see that older people are spending more money than younger people in the example on desserts. So if, for example, there was a difference of 1 cent, if there's only a difference of 1 cent, is that significant? Is it statistically significant? If it was 5 cents, would that be statistically significant? Or would it be €1 more that would be statistically significant? So how do you determine significance? How do you know if it is statistically significantly different? Okay, or is there just a tiny little difference? Okay, so what we're saying here is that is the fact that there is a difference between the means significant or not, and we have to use a test to determine whether it is statistically significantly different. Okay, and we need to work out how we decide which of the many tests to use, and we're going to take a look at that now. One of the things you have to look at when you're choosing a test to prove significance is how many groups are involved. So how many different groups are you looking at or interested in the results of, or you're going to analyse? Look at your research aims and the hypotheses to see how many groups you have. Is county important, or are we interested in the difference between Donegal and the whole of Ireland, or are we looking at the difference between Donegal and just Cork, for example? Is it important to look at the difference between male and female? Is it important to look at the different categories of age? And the more groups you have, the more difficult it is to find a test that will work for your analysis, and often the larger the number of people you will have to question. So again, when you're doing research, keep it down to a very small, possibly maximum of 2 groups when you're doing analysis. When you're testing for significance, one of the things you also have to look at is how many variables you have. And the more variables, usually the larger the sample you need to have, and the harder it is to find a test that will work for your case. So, for example, the price paid for dessert might be one variable. Then if you also wanted to take into account the price paid for the meal or the type of dessert chosen, they would be additional variables. And also then you need to look at what types of variables do we have. Do you remember we had the 4 different data types? Okay, we'd nominal, we'd ordinal, we'd interval, and we'd ratio. Okay, and you need to look at what type of variables it is you're looking at, and that will determine which type of test you can use for your research. So here are a list of the most commonly used tests that are used to test for significance. Okay, so up here you can see this is for 2 groups and this is for more than 2 groups. So how many groups do you have? And here are your variables and the types of variables you have. Okay, so interval and ratio variables. There you tend to use the independent t-test if you've got 2 groups, and if you've more than 2 groups you use the ANOVA test. So if you've interval and ratio tests are variables, and it's the same sample, so you're testing thing on a repeated basis, then you tend to use the matched pairs t-test or the repeated measures ANOVA test. If you have nominal data, okay, named items or named variables, then it's the chi-squared test. With more than 2 groups, again, you're using the chi-squared test. If you've got ordinal variables, which are generally not normally distributed, then you've got the Mann-Whitney-U test or the median test. With more than 2 groups, you've got the Kruskal-Wallis ANOVA test. So you don't just choose a test. The type of analysis you're doing will determine which test it is you can use, and you need to make sure that whatever test you're using is appropriate not only for the numbers of groups that you have, but also the quantity and the types of variables that you have. Okay, looking specifically then at t-tests, sometimes it's easy to observe a difference between two means using, for example, the bar plots that we were looking at previously. But again, you use a t-test not only to show that there is a difference, but also to prove that there is a statistically significant difference between the two means. The t-test is a maximum of 2 groups. And we're going to use that. So again, the t-test is used to measure the amount of difference between two means that you can expect to see due to a random sampling or chance sampling. And the measures are based on the size of the samples. And the results will be looked up in a table, and the table will give you an answer, and usually with the analysis tools you use, it'll tell you whether it is statistically significantly different or whether there isn't a significant difference between the two groups that you're looking at. So for example here, you have sample A that you're looking at, for example, the younger people in the group or the older people in the group. And here is the mean of sample A. And here is the mean of sample B. And your t-test will tell you, while you can see that there is a difference, is it statistically significant, the difference between the two groups. If you've got more than 2 groups to look at, then you can move into an ANOVA test. You've got a one-way ANOVA test which compares more than 2 populations using one factor or one variable. And the two-way ANOVA is comparing more than 2 population means using 2 factors or more. The reason for doing an ANOVA is to see if there is a difference between the two groups on some variable and proving that it is statistically significantly different. So for example, is there a relationship between how students in tutorial do and how they do in the final exams? For example, you might have data on student performance in an honest test tutorial exercise as well as their final exam, and you're interested in seeing if the tutorial performance is related to the final grade. An ANOVA test allows you to break up the group according to the grade and then see if the performance in tutorials is different across these grades. Okay, so one way between groups. The example that we've just described is called a one-way between groups model. You are looking at the difference between the groups, and there is only one grouping, which is final grade. So you're looking at the final grade and you're looking at the performance in the tutorial against it. One-way repeated measures. So this is similar to the last one, except that you have a repeated measure ANOVA when you have a single group on which you have measured something a few times. For example, you may have a test of understanding that you hand out to learners. You give this test at the beginning of the topic, at the end of the topic, and then at the end of the whole subject or module. Okay, you would use a one-way repeated measures ANOVA to see if student performance on the test changed over time. Okay, so one-way repeated test ANOVA test. Two-way between groups are used to look at sort of complex groupings. For example, the grades by tutorial analysis could be extended to see if overseas students performed differently to local students, or to see if culinary students perform differently to tourism students. What you would have from this form of ANOVA is the effect of final grade, the effect of overseas versus local, or the effect of culinary versus tourism, and the interaction between final grade and overseas versus local. So each of the main effects are one-way tests that we talked about previously. The interaction effect is simply asking, is there any significant difference in performance when you take final grade and overseas local acting together? The two-way repeated measures in a similar way to the one-way repeated measures is simply when you're looking at this effect over time, or you're repeating the same test. So this version of ANOVA simply uses the repeated measures structure and includes an interaction effect. In the example given for one way between groups, you could add gender and see if there was any joint effect of gender and time of testing. I.e., do males and females differ in the amount they remember and absorb over time? So, in summary, depending on the type of data you have and the number of groups you are comparing, you have to choose the correct test. So you need to calculate the number of groups you have. You need to carefully analyse how many variables you have and what type of variables they are, and depending on what you can see in terms of the number of groups, the number and type of variables you have, you must choose the correct test that is appropriate for those groups and variables. Now, if you don't do this correctly, then the statistical analysis you have carried out has no basis in fact. It wasn't correct to use those tests, so the results you produce have no validity. Okay, so here's a sample question. So question 1, a correlation allows, option A, allows you to compare more than two population means using two factors plus interaction. Is a single number that describes the degree of relationship between two variables. Allows you to compare more than two population means using two factors plus interaction. Is a set of statistical measures of the amount of difference between means that you can expect to see due to random sampling. Okay, when you're ready, hit down arrow to see the result. So a correlation is a single number that describes the degree of relationship between two variables. Okay, another sample question. A simple frequency table will put all of the data into order, immediately showing the lowest and the highest. That's true. Something is a table that shows the number of data observations that fall into specific intervals. Is it a histogram, a percent polygon, a frequency distribution, or a Pareto chart? It's a frequency distribution. Okay, question 4. A statistics lecturer kept attendance records and recorded the number of absent students per class. This data is displayed in the following histogram with the frequency, here, days, of each number of absent students shown above the bars. So the question is, how many days were there no students absent? Was it 13 days? Was it 100 days? Was it 9 days? Or was it 160 days? It was 9 days. And we can see here, number of students absent was 0. There were 9 days where the number of students absent was 0. Okay, question 5. The following chart shows the annual spending per person on chocolate in 2011. Okay, so the annual spending per person on chocolate in 2011. And we've got Norway down here, we've got Ireland, Switzerland, United Kingdom and Austria. This chart is an example of a horizontal bar chart, stacked bar chart, clustered bar chart, or vertical bar chart. Okay, make your choice. It's a vertical bar chart. Question 6. In statistics, in a negative relationship, high values on one variable are associated with high values on the other, and low values on one are associated with low values on the other. Is this true or false? It's false. So it's exactly the opposite. So a negative relationship says that high values on one variable are associated with low values on the other, and low values on one are associated with high values on the other. Okay, this is the end of this presentation.